Hi, my name is Ben Schenkel. I'm a PhD candidate at Florida State University, and my research here is looking at tropical cyclones and their large-scale interactions going on here. So what we've done here is we've looked at a particular subset of tropical cyclones, in this case major hurricanes within the western North Pacific. And so we're looking at what the response on the large scales are here. So what I want to show here is, first off, we have I've computed the box average anomaly TC, and what it shows is the time evolution of the atmosphere prior to after TC passage. So we have negative 60 days to 60 days. And what you see here is that prior to TC passage, there's no anomalies near the center of the domain. TC passes, but as the TC itself passes, these 1,200 hectopascal thickness anomalies become positive, and we know that thickness anomalies are a proxy for virtual temperature, which gives you an idea of the moisture and the vertically average moisture and temperature within the atmosphere. So you can see that we have these positive thickness anomalies that we'd associate with the passage of the TC itself, and that as the TC passes, we have a cooling of the atmosphere denoted by these negative thickness anomalies that last up to 60 days after TC passage. So this is a long felt response here. Again, what we have here is this is our SST response, and it's showing that our SSTs are near climatology here, and that as the TC passes, we have our negative SST anomalies that occur, and that's just associated with our cold SST wake that you would expect as the TC passes. And we note that they're about 0.5 sigma even after the TC passes 60 days or so. So the TCs are exciting the atmosphere and the ocean on a large, long and large small scales. So next what I'll show you is I just want to give you an idea of, in 3 dimensions or 4 dimensions, how these anomalies behave. These are box average anomalies, but you can see that here I have my 1,200 hectopascal thickness anomalies, and this is my composite domain, a storm relative composite domain centered on the TC, and we see that day -10 relative to TC passage, we have this dipole that's occurring. We have these positive thickness anomalies and these negative thickness anomalies. We see as the TC passes that we have these large thickness anomalies, as we'd expect, associated with the positive and warm air of the TC, but that interestingly after the TC passes we get this large scale negative thickness anomalies, and that's indicative of either cooling or drying that's occurring. So it's not just the SST wave that's going on here, this is a response on thousands upon thousands of kilometers here. So the TC is really interacting with its large scale environment. It's not just a local response that's going on here. And as to what this is, what this dipole is, what this response is, we're not sure at this point. That's going to be reserved for some work in the coming months, but we hope to look at that. I'll skip over here just out of, in interest of brevity. We want to look at this response in terms of, we looked at these normalized anomalies, but we want to look at this from an energy perspective, okay? So what I've computed here are raw anomalies, latent heat anomalies, and these are about 500 kilometer bucks centered on the TC itself, on our storm relative domain. And so you get an idea of how these anomalies, they're entered in the troposphere. Because prior to this, we weren't sure, do TCs on average, how do they modulate the troposphere? Do they warm it on average? Is that more important, or is the drying more important? From these energy calculations allow you to do this. So what we've seen here is that you have these negative latent heat anomalies indicating that the atmosphere is anomalously dry prior to TC passage, but it becomes much, much drier, telling you that the TC is really drying out the atmosphere after it passes. And so this is actually, here are latent heat anomalies indicating the drying. We see that's more important than your potential energy changes or your sensible heat changes. So the drying is more important than the warming. That's what we're showing here. And you can see that it's mostly located within the lower to middle troposphere in this case. So again, what you do, next we look at, if you vertically integrate these anomalies, you can kind of get a number that shows you how these latent heat anomalies vertically or from an integrated aspect impact the atmosphere. So you see that prior to TC passage that your anomalies are near zero. As the TC passes, they reach their most positive magnitude because the atmosphere is anomalously warm and moist. And then after TC passage, again, we have negative moist static energy anomalies denoted by this blue line, but that our latent heat anomalies are responsible for most of that moist static energy anomaly. So it's telling us that the drawing, again, is most important here. So what I did is, and I've shown this for category 3 to 5 hurricanes in the Western Pacific, category 1 to 2 hurricanes in the Western Pacific, and tropical storm. So then I thought, if I have this number, and I can take the minimum or the net change in your energy anomalies as the TC passes, can we make a back-of-the-envelope calculation for what the net energy transport is associated with the TC? So I used these numbers, and I took the given number of TCs that recurve in a given year, and I calculated the net forward energy transport, assuming something. And what we came up with was a number of 0.01 petawatts. Now, to give you an idea, the peak meridional energy transport is about 5 petawatts at a given latitude band. So that seems to me to indicate that TCs, recurving TCs, only result in a small portion of the energy transport for a given year, and that if you look in the ocean, this number is actually much higher for oceanic heat transport induced by TCs. That's on the order of about 0.5 petawatts or 1 petawatt. So what this indicates to us is that TCs are more important in the ocean than the atmosphere. But again, this is a back-of-the-envelope calculation, so we have to do some more conclusive calculations.